I'd like to thank you, organizer, Professor Yu and Professor Han, to the invitation of this conference on the occasion of Professor Burns' 65th birthday. Actually, I have been to his talks twice, and both talks were about the symplectic quotient, and I'm glad that my talks today is also about symplectic quotient. So let me give my setup for symplectic quotients. People going to talk about the word crossings of twist Quiver bundles, because I have to give some motivation for the introduction of the twist Quiver bundles, and that will be arise from the Nakajima's Quiver variety, which is a special symplectic quotients. So so W is going to be a affine variety. Say with action by complex reductive Lie group. And suppose it acts linearly in the sense that the W can be embeddable to some linear space such that this action acts through general linear group of Cn. In this setting, we like to define some quotients of W by G after introducing some character theta. So theta is character. I.e. it's a homomorphism from G to group C star. So usually this reductive Lie group in my examples usually general linear group of some vector space or their product. So that in this case, general linear group case, theta is going to be usually determinant, and in the product case, it's going to be just product of a determinant or powers of some determinant. And then the definition of this one is as following. So we like, first of all, consider W as some product of trivial line bundle on W. Then this I'm going to take this one as this the ring of polynomial functions on W times C. Then if we take a product of that one, we'll get a W itself. But we like to take a quotient, so why not just take the product of G invariant part of this ring? So take a G invariant So that's the definition of this quotients. Here, I have to specify how group G act on C, that will be acted by that character theta. So for example, then maybe I have to give us some examples. So W is just C, 3 acted by C star, that's our G, with the character 2, -2, 1, 1. So here, this means that the T going to be acted by multiplication by exponential of, T minus 2, T and T. Then take the theta is just the identity. Then one can see that these quotients tends to be isotropic to cotangent boundary of CP1, which is also usual quotients of following set. C times 0, 0. In fact, this locus has a name, and this locus is called stable locus, or in this case, that's also equal to semi-stable locus with respect to theta. And then just let me just assume that there's some such notion to talk about a point in the W is theta stable or theta unstable, or theta unstable, or theta semi-stable. And if a theta stable, it's going to be semi-stable. And in general, these quotients in the good case, it's going to be equal to the orbit space of stable locus. If WS is. So through my talk, let me assume that this is the case because of the following reason. With respect to theta, and assume that the group G action on the stable locus is free action. So that the W as my G, so our quotients is smooth. So there's no orbifold point here. And also this projection map WS to this orbit space is a principal G band. That's the principal G band. So this kind of picture, I'm going to use it to study holomorphic map from the curve to that quotient. So from now on, I'm going to interested in the considering map from X to this quotient. So this is a say this is maybe say Riemann surface. Then using that G principal bundle, we can construct principal bundle on X by pulling back that one, some P. And since it's a pullback, we have a map from here to here. It's a bundle map. This is a bundle map. In other words, G equivalent map. And this is a principal G bundle. So this picture motivates to consider following notions, so-called quotient map to the quotients. So define. Is our pair P and X, P and U. So I have got the from domain X. Such that the P is principal G bundle and U is a G equivalent map from P to W. Since it's not required that maybe this image of U might landing on, it might be contains an unstable point of W. So that in generally, this quotient map is not a definer map from X to the quotients. So that's the reason why we call it it's a quotient map. And but we like to control the such kind of map by requiring that the quotient map is called stable if generically it lands on the stable locus. So in other words, it defines if it defines a rational map X to W G. But still quotient map, even though it's not a really defines a map to the quotients, it has some nice property that if we collect all stable quotient map, which I'll denote by Q map to X to W G. So this collection of all the space of stable quotient map. it turns out that this has a very nice property that this is going to be complex space, actually some kind of algebraic space, which is proper over affine quotients, and also, in a sense, it's a smooth, virtually smooth. So this theorem is T2. Oh, so here, I'm sorry, I have to. So theta equal to 0 case, trivial case. So, so when theta equal to 0, 0, it's 0. So G act on C trivially. So this is trivial character. If you choose trivial character, then the this quotient is nothing but equal to just spec of CWG. So in the example, where the C3 act on the C star by -2, 1, 1, and then take a zeta equal to 0, then that case, you can see easily that the CW, the invariant polynomial is nothing but the, let's choose coordinate x1, x2, x3, and this one is generated by x1 squared, x2, maybe x1, x2 squared, x1, which has presentations by 3 UV, maybe small w, with the relations v square is minus w, u, so uw, so that it has some cone singularities. So that case, this becomes that cone, which looks like that one. And then when theta equal 1 case, this was subject to cotangent boundary of CP1. So actually, it's just this map is a contraction of geolocus of CP1. So this is CP1. So in the beginning, I mean, generally speaking, we had some GIT quotient, some kind of symplectic quotient or GIT quotients for some non-trivial theta, so that this is going to be smooth. And in generally, this may not be compact, but it's going to be compact over this affine quotient always, affine quotients. So like this picture, I mean, every p-image is compact. So it's this variety is proper over that affine. This is called affine quotient. And this theorem says that if we collect all stable quotient maps, that's going to also compact as much as target is. because it is proper over also affine quotients. So that this notion, I mean, the stable quotient map will give another way to compactify holomorphic map from curve to this Riemann surface to GRT quotients. And they have some many applications, and today I'd like to show one of it, one of them. That just let me give some remark that the in the stable map compactification, so M bar. So let me say it this way. I mean that here, so you have a X Riemann surface, and this stable quotient map defines a rational map from here to quotients. But at some point, at some finite point, it's not defined. So this point is kind of a base point. But in the Gromov compactification, instead of this base point, we have to introduce some kind of bubbling, sphere bubblings. So I'm saying that in this compactifications, instead of having instead of changing domain curve, don't change the domain curve, but it just blow down the all sphere bubbles to create some finite number of base point where this map is not well defined, but they keep track of the principal bundle and also section U to control the space of all such data. So good thing is about this compactification is that we can keep the domain curve X. Yeah.
Why do you put the sphere?
Why do I put sphere? I mean, if you want to use Gromov compactification, then you have to allow the bubbling, right? I just want to compare this compactification with a stable map, compactification. I mean, here there's an honest. This contains a usual holomorphic map from X to W mod G. So usual holomorphic map is also stable quotient map. And there's another way to compactify it using stable map complication, right? I'm sorry?
Two compactifications different?
Yeah, they are different. Yeah, totally different, yes. So I like just they could emphasize that in the quotient map complication, we just fixed domain curve X. I mean, this is not going to be changed at all. But in the stable map complication, sometimes domain curve X allowed to have some kind of sphere bubbling, right? So I like to apply this to the holomorphic symplectic quotient case. Suppose that this is holomorphic symplectic. In other words, there is some holomorphic symplectic form omega, two form omega, non-degenerate, which in particular making these two bundles isomorphic. That case, I like to just to consider deformation space of a map from X to M. Okay. So given, and let's think about deformation space. At this point. So we like to deform this given holomorphic map F to the holomorphic symplectic quotients. Then deformation space. So it's nothing but the zeroth cohomology of that one, and so the obstruction space is H1 over X F Tm. But using this identity, we can write it. This one is H0 over. So this is M, and so now using set duality, that's isomorphic to the actually dual of obstruction space. So this deformation space isomorphic to dual of obstruction space by set duality. So after adding the tensoring with the canonical line bundle of X. Sorry. So this, and suppose X is elliptical, so suppose this is elliptic. Then this is just X. So that this space is exactly obstruction space. Okay. So deformation of space has some kind of has a symmetry, and it's called the moduli problem. Moduli space of mapping from map to X to M has symmetric deformation obstruction theory. So in other words, the obstruction is isomorphic to deformation, dual of deformation. So given elliptic curve X and the holomorphic symplectic manifold M, we had this picture. But this space is not compact. Now, if you use stable map compactification, the domain curve is going to be changed. And that ruins this symmetric property. That will, but however, if we use the quasi-map compactification, and still we can keep the same domain curve X, and also we have some kind of analog of the tangent band, which has this kind of property, so that symmetric observation theory still hold. So that's the one of the advantages of stable quasi-map compactifications. Sorry? So more precisely, maybe to say TM. Yeah, and then they take the dual of it. Yes. So this set duality say that these two are isomorphic, elliptic curve case, right? So many holomorphic symplectic quotients can be obtained by Nakajima's Quiver varieties, actually. So to define it, let's just say about quivers. So quiver Q has data Q0, Q1, and T and tail map, head map. So this is collection of vertices, and as this tail map, head map. So example. So Q0 in this case is 0, 1, and the Q1 is 2S, A, B, and A. And the TH is a map from Q1 to Q0. So for example, TB is B has a tail 0. So head map is 1. So that's example. So given quiver Q, let's define double quiver Q bar. Just adding the, just doubling the arrows. Just add the opposite arrow for each arrow over Q. So this example. So same number of vertices. Vertices are same, 0 and 1. But we have this original arrow, then just add another one, but opposite one. A, let's call A minus B, and B minus. Okay, so now we have a definition of quiver, and then so people going to define the quotient. We have to introduce also let's see, a dimension vector. So if we so for each edge, for each vertices, let's assign the non-negative numbers, non-negative integers. Let's see, for I, just v sub I. This will be called a dimension vector. And let's fix also some distinguished vertice. Some distinguished one. With that data, we like to consider holomorphic symplectic just vector space, which is defined to be just a linear map homomorphism from C to D. Generally, let me use C to D, V sub I, tail to head. So this each term, I mean, each component is a collection of a matrix, right? That's a collection of a matrix. And we collect all sum over each edge on the double quiver. But double quiver has arrows, paired arrows. I mean, the original one or negative one, A minus or B minus. So that this has can be written as direct sum of two identical, some kind of a, no, not exactly identical one. I mean, two vector space, but has the same dimension, but they are dual to each other. So that this one has can be written as cotangent bundle of V plus, which is has a holomorphic symplectic form, the standard one. It has the standard linear form, and also this vector space has a Hamiltonian action by product of a general linear group. By adjoint action, I mean, this is a linear map from here to here, right? So group G going to act on domain space and also target space in the standard way, and so this whole product group G has action on this linear space, and it turns out that this action is a Hamiltonian action with some moment map. So mu sending the phi A to so phi A is a collection of matrices. So that's element in here, and then just send it. This one is summation of phi A. So take just the matrix product of phi A minus, so phi A minus. Sorry, Papa. Let me. So A bar means the opposite one. I mean the opposite over A. Sorry. So now we would like to define the quotients. So given character of group G, define holomorphic symplectic quotients. So this called. By just taking the inverse image of a moment map, this particular moment map at the 0, and so this is going to be some affine variety inside of this linear space, and then now take usual GRT quotients by group G. So this will be called Nakajima Quiver variety in my talk. So now what I'm going to do, consider just consider just Cauchy map to this quotient. So a Cauchy map. So that's will be nothing but following one. I mean, principal boundary P left P0 and then X this data, right? And this data was equivalent following data. So mu inverse 0 in particular is inside of that V plus V minus this space. Before going that, from principal bundle, let's construct vector bundles EI for each vertex I. So define P times G of this representation of group G, C, V, I. So group G act on here standard way, just standard action. So principal bundle P will give rise to collection of a vector bundle for each vertex I. And this equivalent map U going to introduce a bundle morphism from ET8, E header A, some bundle morphism. But the image is inside of this locus. So it should satisfy certain this relationship, summation of phi A bar must be 0. So so sometimes I like to call this one is a moment map relations. And we can go converse way. So this is they are equivalent notions. So now forget about the notion of Cauchy map and just consider this this data, and we like to call this data as Cauchy. Sorry, the Quiver bundle. So usual bundle going to be just a bundle on this Quiver, this trivial Quiver, Q, just one. It has only one vertex, no arrows. But the whenever some interesting Quivers structures, this data also collect also bundle morphism between the vector bundles associated to each vertex. So now let me define the following date. So now so give for twisting on such data so that so that the for any so that the following the obstruction theory, the deformation obstruction theory is symmetric. So from now on, X will be any Riemann surface, not necessarily elliptic curve, so that it might has non-trivial canonical line bundle. According to that canonical line bundle, we like to twist some data of actually bundle homomorphism, such that the still deformation obstruction theory for such twisting collections is symmetric. So I'm like to consider some modular space of all twisted Quiver bundle. So this is After once fix the quiver and the dimension vectors, this v sub I, and also so rank is dimension vector v sub I. And also degree, let's fix the degree of EI is DI. Then this modular space too much big, so we have to talk about the some stability conditions, some stable twist Quiver bundle. The one stability condition is given by the so-called stable Cauchy map. So we like to call that this Quiver bundle is stable if it is stable as a Cauchy map. So that's the one stability conditions. And it turns out that there are many other ways to give stability conditions depending on the parameter tau in the positive real number. And that what can be proven is that the stable or sometimes semi-stable is the following. So for large tau, we have absolutely. I have to define the so this is just slope stabilities, so that some twist Quiver bundle is tau stable or tau semi-stable or unstable. We could talk about such thing. And for large tau, this notion is exactly coincide with the stability conditions for Cauchy maps. For stability for Cauchy map, there's no notion of semi-stability. So that for large tau, for large number tau, when the tau becomes very large, the semi-stability equals stability. There's no strictly semi-stable ones. And so using this thing, one could prove that there is only finite worlds in our tau 1, tau k in our positive, such that the tau semi-stability is exactly equal to the notion of tau stabilities if tau is not tau I. Some real numbers. I'm sorry, I cannot define exactly what I mean by slope depending on tau. I like to define there's a notion of So tau is some positive real number. For each positive real number, one has some notion about following one. For a given twist Quiver bond, we can determine that that's a tau semi-stable or tau stable or tau unstable. And that such kind of notions are usual one when tau is large enough for a given numerical data, V and D. And that now what I want is that the to compare the some Euler numbers of that modular space M as tau. So this modular space, so suppose we have a wall, two walls like that. And when tau varies here, from here to here, I mean in this interval, when tau varies, this modular space remains the same. But the when tau crosses the wall, this wall tau 1, this modular space is going to be generally changed, to so topologically different space, and so on. Also here, we have we got a different space. Like most theory, this is kind of a critical point of most function. So something interesting changing occurs at this wall, only this wall. So now we like to describe the topological Euler characteristic of say tau minus 1 with the tau plus. We like to compare these two. So we like to, for example, express this one in terms of therefore minus plus. If one could find some formula, it's called the word crossing formula. And the good thing about the word crossing formula for topological Euler characteristic is following. The topological Euler characteristic is has property of additive property. This is some kind of a variety. We like to think of this one as a kind of a space, and this one, and that's another space, but they have some common region. So that the Euler characteristic of this one is additive in the sense that the Euler characteristic of this whole thing, this one, is Euler characteristic of that plus this one.
Those two things birational if you go across the wall. And then the common points might be parts that don't have to be blown up or blown down.
Yes. I think that's true in the most cases. But actually, I constructed this modular space not using GIT quotients. If they defined using GIT quotients, they are supposed to be bilateral to each other. But I don't know the exact answer for this particular spaces. So actually, I defined that one as a kind of a stack, actually. You have a big chunk of common one, and you have some smaller ones, and these smaller ones can be described by following way. I mean, this is a tau minus unstable part. In the top plus sense, that's a stable, but in the minus sense, it's not. So that using so-called Harder-Narasimhan filtrations, there's some description of this space in terms of some smaller space of this kind of thing. M tau minus, but the V prime, this will be different, V d double prime. So there's certain description about this that difference, and that difference can be written like some projective bundle over extension of E, also E1 and E2, and the Euler characteristic of this one is, of course, depending on dimension of this one, right? Only depending on dimension of that. So that there's some kind of a Wilkerson formula can be, roughly speaking, obtained by using inclusion-exclusion principle. But for the precise, rigorous, for the rigorous proof, one have to define the Euler characteristic of that modular space even at the wall. I mean, at the tau I, sorry, tau maybe 1 or 2, yeah, tau I. And this is some very bad space in the sense that it's called the Artin stack. And the topological Euler characteristic is defined by Joyce, also Song. So one have to define this thing to talk about more precisely the word crossings. So we need that choice of song theory. And on the other hand, for this particular examples, we need ideas of the idea of and the pen, who worked out the word crossing formula for ADHM Quiver case. ADHM Quiver case. So using those things, we obtained some kind of word crossing formula. sorry, I cannot write it, but this is a joint work with Yu Young. Okay, so I'll stop.